Hello students, welcome back. This is going to be the lecture that is part of this module that's just sort of an overview of the physics of meteorology about temperature. I'll be honest, this is not the hardest material in the semester by any stretch. It's more, in the plan for the course, this is more about just making sure everybody's on the same speed about the instruments and the effects and so on about these phenomena. We'll learn a little bit more in the next lecture that's about how heat is transferred through the atmosphere that's a little bit more complex. But this is just part of a set of ideas that we're having about surface weather and how surface weather is going to be influencing electrical load and yield. And over the course of the next few online lectures, you're going to be seeing the effects of temperature, humidity, pressure, moisture, clouds and precipitation, winds, and so on. All of these, of course, have different ways in which they can directly or indirectly affect both the load on the electrical grid and the amount of power that can be produced by solar panels or by wind turbines or whatever. And this first lecture, like I said, in this part of it is just about temperature. Of course, if we're just talking in the context of electrical load and yield, the main way in which we're worried about temperature is how it affects the rate of heat loss or heat gain by different structures. I mean, of course, in the winter, the colder the weather is, the greater the electrical demand there's going to be for electrical heating, and in the summer, the higher the temperatures, the greater the demand will be for air conditioning. And temperature is going to also have an impact on the production of power through renewable resources, although it's going to be a less direct effect. For example, the amount of power that can be produced by wind turbines depends in part on the density of the air that is at the time passing through the turbine, and density is determined in part by the temperature of the air through the ideal gas law, which we'll be getting to at some point too. But for now, you know, the effects of temperature on production of power by wind turbines is hardly huge. In the same sort of way, there is some effect on like the efficiencies of solar cells, but you know, especially under extreme temperature ranges. But you know, that would be a bit more specialized than what we're looking for here. Even grade school science students tend to know the temperature is about how molecules are moving. More strictly speaking, though, the temperature is actually directly proportional to the average kinetic energy of the molecules in a substance. Kinetic energy is different, of course, than just how they're moving. Kinetic energy is related to mass times the velocity of the molecule squared, so the mass of the molecules are important. Light molecules have to move a whole lot faster than heavier molecules to have the same amount of kinetic energy. Air is a mixture of gases, each of which has a very different molecular weight, and so the velocity of the molecules will be different for them to have the same kinetic energy. So a sample of air will have a mixture of nitrogen molecules and oxygen molecules and carbon dioxide molecules. The lighter molecules, to have the same temperature as the heavier molecules, the lighter molecules have to be moving faster. In an interesting little development, that's actually why you don't find gases like hydrogen and helium in the Earth's atmosphere, because those very light gases have to have a very high velocity to have the same temperature as a relatively heavy molecule like nitrogen or oxygen. And in practice, the speed that a hydrogen molecule or a helium molecule needs to have in order to be at the temperatures we experience on Earth is greater than the speed of those molecules is greater than the escape velocity of Earth. In other words, if those molecules are sufficiently high up in the Earth's atmosphere so that they, you know, won't necessarily bump into any more molecules as they're moving, they're actually moving at escape velocity and would leave Earth's gravity well. This is why you don't have gases like hydrogen and helium in any measurable quantity in the Earth's atmosphere. Now in the next lecture, we're going to talk more about different ways in which heat can be moved around in the atmosphere, but from the point of view of just electrical load and yield, the one that we're going to be most worried about, at least directly, is going to be conduction. Conduction is going to be the transfer of heat between objects that are touching and have different temperatures. And I always like to use a piece of clip art associated with pool balls when I'm talking about conduction, because it kind of works that way. I mean, the kinetic energy of the cue ball is transferred to the other balls on the table when it collides with them. And in the same way, you know, conduction physically happens as molecules in one material bump into molecules in the other material and transfer their kinetic energy from the material that has their molecules have on average more kinetic energy, that is to say the hotter material, into the material that on average has lower kinetic energy, that is to say the colder material. And so these high-speed molecules collide with the slow ones, increasing their kinetic energy, increasing their temperature, but that of course removes kinetic energy or heat from the hotter material, lowering its temperature. Now, in the context of electrical load and yield, we would be thinking of conduction then as being an important way in which heat escapes from a structure like this house right here. It can be a major way in which buildings lose heat. I mean, heat is directly conducted through the walls of the building, through the insulation. That's why we put insulation in the walls, because insulation reduces the rate at which conduction can happen. In meteorology, we would call that, it reduces the sensible heat flux. And so this transfer of heat through the walls is a type, is diabatic conduction. Now, of course, there are other ways in which heat is lost from a building, that is not directly conduction. It can be lost, for example, through leaks and so on. That's actually, strictly speaking, a type of advection, which we'll learn about in the next unit. But you could simulate it. You could model the process as conduction, and in fact, it typically will be. The heat being lost by the leaks in the building is going to be proportional to the heat being lost by conduction anyway, so you just sort of add the two factors together. Obviously, temperature is measured by a clever device called a thermometer. You can in fact thank our good friend Daniel Fahrenheit, who invented such a device about 300 years ago, something like that. Obviously, you know how thermometers work, but in practice in meteorology, real mercury or alcohol spirit thermometers are not used very often because they're fragile and hard to calibrate and so on. Typically, they're actually done using electronic thermistors and so on at a weather station. What the thermometer is actually measuring, of course, is its own temperature. It's the temperature of itself. That's just the nature of thermometers. That's why when you take a thermometer out of the warm house and you take it outside on a cold day, you have to let the thermometer adjust to the temperature of the air around it, because otherwise you're just getting the temperature of the thermometer, not the temperature of the air around it. And in fact, air temperature is what we typically want in meteorological applications. You in general want to have the temperature of the air. The temperature of the thermometer itself is not what's terribly important, but since that's what you're going to get, you need to make sure that the temperature of the thermometer is the temperature of the air. How do you do that? Well, you're going to need to be very careful about where you put the thermometer that is measuring the temperature. This picture here shows some examples of different temperatures that would be obtained if you had your thermometer poorly sited. Oops, sorry, I dropped my notes here. In fact, after this video, there's going to be a short little fun video I recorded with my 5-year-old that just shows the importance. We were going to put a thermometer in different areas of our yard, and you're going to see how important proper sighting is so that we can get the thermometer to be reading the temperature of the air and not something screwy. Because the sighting of the thermometer is important. It needs to be in an open area over a surface that doesn't influence the temperature directly. For example, if you have the thermometer just sort of like out over a dark surface that's absorbing a lot of light from the sun, the temperature there is not going to be very typical of, say, the temperature over a more open area like a grassy area. The thermometer also needs to be shielded from direct solar radiation. You don't want it to be in the sunlight itself, because the thermometer itself will be absorbing shortwave radiation. You're going to see that in the video with my son. We're going to move the thermometer out into the sun. When this thermometer was in the shade, it's getting us the temperature of the air around it. The primary way in which the thermometer is gaining and losing heat is by conduction with the air around it, so the thermometer reaches the temperature of the air around it. When we put the thermometer out into the sun, then the primary way in which it is changing temperature is by absorbing radiation from the sunlight, and therefore it's going to have a much higher temperature. And I think the results actually turned out to be fairly impressive, but you'll need to watch that little video to see. So a real operational meteorological thermometer is typically shielded. It's typically shielded by being inside of a little white, kind of like a birdhouse looking thing. It's called a Stevenson shelter, actually, but it's just sort of a little ventilated, shielded house that allows air to flow through. It looks like a birdhouse or something like that. They're always full of wasps and things like that too, but that's okay. The sensor is inside of this little house here that shields it from direct solar radiation, yet allows it to be ventilated so that it can experience the temperature of the air. poor sighting and shielding of thermometers is why, like, bank thermometers tend to be so far off. When you drive past a bank, you almost always notice that the thermometer on the bank is telling you a very different temperature than, like, the, you know, like if the radio just told you that, you know, currently it's 85 degrees in Omaha, and you drive past the bank and it says it's 104. No, it's because the thermometer on the bank is poorly sighted and shielded. They usually aren't that far off, but they can be very far off because they just have the thermometer sitting out in the sun, and it's registering a temperature that is the temperature of the thermometer, but that has nothing to do with the air temperature. And it's the air temperature that's going to be determining the rate of heat loss by things like conduction and so on. Okay, so that is enough just kind of for the basics of temperature for now. We're not going to get all bogged down yet in like thermodynamics or rates of heat flux across, you know, materials or anything like that, so that we can start thinking about things like estimating electrical load or anything like that. I just wanted to kind of have a quick breeze through the temperature. Now in the next lecture, we're going to be talking about the factors that determine the rate of heat. Well, we're going to be talking about the factors that are about moving heat around in the atmosphere, including like sun-earth geometry, where you're going to be learning about like sun angles and so on. Okay, please let me know if you have any questions after this short lecture. This has been Dr. John Schrage.